Welcome. This is section 310, which is just like a brief introduction to linear approximation. So remember we have an equation for a line, right? Way back in Algebra 1, y minus y1 equals m times x minus x1. Or if I add the y1 to both sides, we could rewrite it as y equals y1 plus m times x minus x1. And in previous lessons, we've talked about finding the tangent line to a curve. So let's say that curve's name is f of x, and let's say we want to find the tangent line to f of x at x equals a. Well, if we do that, my f of a is like my y1. My f prime evaluated at a is the slope, and x1 is a. So this is just like the equation of a line, right? It's just the tangent line to a curve. Now, if we look for values near a, the output of my tangent line is going to be really close to the output of the actual function. So we could say that our tangent line is approximately the actual function. So what we'll do is we'll call that tangent line then a linear approximation of f of x. We'll give it the name L of x. So looking at a picture here, so the blue line is our curve f of x. The pink line is our linear approximation L of x. And as long as we're looking kind of near a, L of x gives us a good approximation from f of x. The further we get from a, the worse that approximation gets. And specifically for a specific value, if I look at this distance between f of x and L of x, that's going to represent the error in my approximation. So let's look at a specific example here. So it says find the linear approximation of the function f of x equals square root x plus 3 at a equals 1, and use it to approximate the numbers for 3.98 and 4.05, and then are these approximations overestimates or underestimates? We'll look at the error there in a second. So the first thing I want to do is write my tangent line. So I know that x is equal to 1, and then my y is going to equal 1 plus the square root of 3. So the point we're looking at finding the tangent line to is the point 1, 2. Next, I'll need the slope. To find the derivative of square root of x plus 3, that's a tangent rule. So I'm going to think about square root of x plus 3 as x plus 3 to the 1/2. So the outermost function is the exponent of 1/2. When I take the derivative of x to the 1/2, I get 1/2 of times the insides to the negative 1/2 times the derivative of the inside. Now the derivative of x plus 3 is just 1 plus 0. And now my slope then is going to be the derivative of f evaluated at 1. So 1 plus 3 is 4. 4 to the negative 1/2 is 1/2. So my slope for my tangent line is 1/4. So my linear approximation is going to be y plus m times x minus x1. And now I want to approximate square root of 3.98. I have to figure out what the x is for 3.98. So if I go and I use this guy, I can see I can rewrite 3.98 as 0.98 plus 3. So the x there has to be 0.98. Likewise, for 4.05, the x has to be 1.05. So if I plug these into my calculator, I can see that my linearization gives me 1.995, and my actual exact value was 1.99499, etc. So I can see that this is a slight overestimate. And in fact, if I wanted to, I could look at the total error there. So I can just take this value minus that last value, and there's my total error. Again, error is going to be positive always, so just you can take the absolute value of it or whatever. Or a negative error would imply that we underestimated. A positive error would imply we overestimated. And if I do the same thing for 1.05, we can see that my linear approximation is 2.0125, and the exact value there is 2.0124. So this is an overestimate also. And again, if I wanted the error, I could take my approximate value and subtract the exact, or I could do the reverse and just take the absolute value. But I see that my error there is 3.88. Okay. All right, let's look at the next example here. It says, for what values of x is the linear approximation, blah, 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 accurate within 0.05. If you'll notice, this is the same linear approximation that we just did. It has just been simplified. And this is the same function. So this is like my f of x. This is my L of x, and I can tell really easily which one is my linearization because this is the linear equation, right? It's an mx plus b. This guy is my error. So what this is saying is that if I take my exact and I subtract my linearization, that difference should be between 0.05. Okay, so let's start by isolating the linearization on the inside here. So I will subtract the square root of x plus 3 from both parts of my inequality. And then I will multiply both sides of my inequality by -1. Remember, that's going to flip my inequality symbol. So these less thans are going to change to greater thans. Same thing happens if you divide by a negative. So let's write it this way. So what I need to do now is I need to find when is this linear function between this function and this function? Well, to do that, what I'm going to do is graph. So I've gone ahead and typed in the left side, the middle, and then the right side of my inequality. I'm going to type in, going to change the option here to make the left side come in as this big thick line, the middle to be the straight line, and the right side to be a dashed line, just so it's a little easier for me to see what's going on. I chose the window, I did a little bit of experimentation to find a decent one, from -4 to 10 on the x, and then -1 to 5 on the y. And then I'm going to hit graph. So here's my upper bound. There's my linear approximation. There's my lower bound. So it looks like from here to here, my linear approximation is in between the two error pieces, my lower bound and my upper bound and my lower bound. So I just need to figure out what these two x's are and then round appropriately. So to do that, I'm going to do second and then trace. I'm going to pick the intersect command. I want both intersections occurring with the thick line and the solid line. So I'll do that. And I will, for my guess, since there's two intersections, I have to be a little bit careful. So I'm going to move over there, press enter. So my first intersection occurs at -6.256, blah, 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 blah. Now, I need to make sure I'm rounding carefully here. So let's say we want to round that to the 10th. I want to make sure I'm rounding in this direction so that my linearization stays in between the two. I don't want to round over here in that direction where it's going to move outside my bounds. So I need a number, I need to round this to a number bigger than -2.65, yada, yada, yada. So I'm going to say round that to -2.6. So that's my lower bound. I'll do second, trace, intersect command, first curve, second curve, still the same. And I'll scroll on over here, or by my second intersection, and press enter. And that other is at 8.65. Again, I want to make sure I'm rounding here to a 10th. So I'm going to round in this direction. So I'm going to round that down to 8.6. So I have then my x needs to be between 2.6 and 8.6. All right, so the last thing I want to talk about here is talking about differentials. So remind ourselves we have some f of x, that's the blue line here. We have some linearization that we've drawn in, that's the pink line. To build that linearization, we made a tangent line to point P on the curve. Now the slope at point P is dy dx. So if I am looking at some point R on the linearization, means we've gone dx over and dy up, because the slope at P was the derivative of f at P, so dy dx. Contrast that, if I look at that same x value, that's dx over on the f of x, we'll call this point Q, we'll call that change in y delta y. So delta y is just going to be the y coordinate of P and subtracting the y coordinate of Q. Will actually be y coordinate of Q minus the y coordinate of P. As opposed to the dy, which is going to be the value of the derivative at P times the change in x. So that's what we've represented here. So dy is equal to f prime of x times the change in x. And again, the f prime, the x here, the starting is the starting value. And here we have the new y coordinate minus the old y coordinate. So let's do an example here. So it says compare the values of delta y and dy if f of x is this and x changes from 2 to 2.05. We're just going to do part A. So this is like my x here, and this is my x plus delta x there. So let's do delta y first. That's just going to be f of 2.05 minus f of 2. Nothing much to do there, so I'll just go to my calculator. And on a problem like this, where I'm going to have to be using the same function possibly a bunch of times and using it to do stuff, I'm just going to type it in one time to the y equals. And then to do this, I'm going to press vars, go over to y vars, pick function, and then pick y1, and do 2.05 minus, and then I'll do the same thing, function vars, y vars, function y1 of 2. So it's just like operates like a function notation. So that's my delta y. And then to do my dy, well, that's just going to be f prime at the start times the change in x, so the delta x, which is 0.05. And this I can also do on my calculator. So remember to do a derivative evaluated at a value on your calculator. Your calculator can do this. So I'm going to do math, and I'm going to go down to the n derive option. Pick that, type in x, because we're doing a derivative with respect to x. Now, I could type this in manually, or remember I had left this in y1, so I can press instead vars, y vars, function y1, and I want to do this when x is equal to 2. So that's going to give me my f prime of 2. I want to take that value then and multiply it by 0.05. So there's my dy. So if we look at the picture here, there's my dy, and the other one was my delta y. So a nice application of using differentials is to do a problem like this. So it says the radius of a sphere was measured to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using the value, or using this value of the radius to compute the volume of the sphere? So I know that volume is, for a sphere, is 4/3 pi r cubed. And if I take the derivative of this with respect to the radius, it's going to be dv dr equals 4/3 pi, are all constants, and derivative of r cubed would be 3r squared. So this just would simplify down to be 4 pi r squared. If I multiply both sides by dr, this is going to be like the maximum error in volume. So if I plug everything in, so radius was 21, my dr is like my possible change in radius. So if I type this into my calculator, I get about 277 centimeters cubed. That seems kind of big, so maximum error is maybe not always the best measurement. What also is quite useful would be like relative error. So to do that, I can take my my max error by the total. So in our case, that's maximum error was dV, and our total would be just the volume. So we'd have like 4 pi r squared over 4/3 pi r cubed, dr. So when I do that, I'm going to have 3 dr over r. So 3 times 0.05 over 21, which is about 0.0024. You might also call this the percent error as 0.24%. So this is our max, and this is our relative, and this is our percent. And that ought to do it. You guys should be able to work on problems 1 through 5 odd, 7, 11, 17, 19, 25, 33, 35, and 37. And we'll see you guys on Monday. Have a good weekend. Bye-bye.